All right, awesome. So let me start my. All right, hi everyone. My name is Brandon, and tonight I'm going to propose my final project on knowledge distillation. Before we get started, I want you to imagine that you have a large model that performs well on your data, and you're interested in deploying that model on, like, for example, a mobile device. But you run into the problem that your model is too large. Now, you could go back and create and train a fresh, smaller model, but of course, that could come with a performance hit. So my question is there a way to package your large model into a smaller architecture without taking a huge performance hit? And the answer with knowledge distillation is hopefully yes. Um, So what is knowledge distillation? Knowledge distillation is a model compression technique whose goal is to transfer knowledge from a large model to a smaller student model without loss of validity. And it accomplishes this by exploiting the loss calculation during training. In this figure, we can imagine that our large model is this teacher model, and the small model is this student model. And what we want to do is somehow distill and transfer the knowledge from the teacher model to the student model. And before I keep going, I just want to show you that the original paper, Distilling the Knowledge in a Neural Network by Hinton et al., has about 20,000 citations according to Google Scholar, and about 15,000 of those are since 2020. So this is a pretty active topic in the neural network world. So before we get into knowledge distillation, I just want to revisit the softmax function really quick, since it's going to be really important. So as we remember, the softmax function transforms some logits into pseudo-probabilities. And for that reason, it's often the activation function of the last fully connected layer of your neural network. And I don't think we covered this exactly in class, but the softmax function has this hidden temperature variable that affects the entropy of the resulting probabilities. So usually we just set this to 1, and then we forget about it. But as we can see in this figure, a lower temperature value results in the probabilities having less entropy, and these are called hard predictions. And higher temperatures tend to have more entropy, and these are called soft predictions. And we can see this by the distribution being more uniform. Okay, so now let's get to actual knowledge distillation. So imagine we have our pre-trained teacher model, and we have a fresh student model. So if we were to train the student model normally, we would feed the model some training data, make some predictions, calculate the cross entropy loss, do backprop, update the weights, and then repeat this over and over and over. However, for knowledge distillation, instead, during the loss calculation, we're going to add an additional loss term, and that's this term right here. In this case, it's the KL divergence between the soft student predictions and the soft teacher predictions, where the temperature is some high number, like 10 or 15. And here, a high temperature increases the entropy of the probabilities, thus providing more information to the student model compared to the hard probabilities. And it reduces the variance of the gradient between different observations, and that allows us to use a higher learning rate. So that's the gist of knowledge distillation. And my goal for the final project is actually pretty simple. So at least in Keras, which is my preferred framework, there isn't already a built-in distiller utility for knowledge distillation. So for my final project, I just want to successfully implement knowledge distillation. And to accomplish that, there's a couple of things that I'll need to do. So the first thing is that I'm going to have to create and train a teacher model. And then I'll have to create and train a student model, just as like a control. And then I'll have to make the distiller utility, and then create and train another student model using that distiller utility and the teacher model, of course. And then I'll go ahead and evaluate and compare the models. In the end, I expect the teacher to have the best performance, followed by the distilled student model, and then followed by the control student. And for some more details, so for this project, I considered 2 approaches. So for the first approach, I considered using a large pre-trained teacher model, something like VGG16, on a more difficult data set like CIFAR 10. However, my early tests have shown that some of these larger models' ImageNet weights, the pre-trained ImageNet weights, yield less than like 80% accuracy, and that's after 20 epochs. And it's really important for the teacher model to perform well for an effective knowledge distillation. So given the time constraint of the project, I think that investing time in training and testing a deep learning model seems less productive than just exploring knowledge distillation further. So the second option that I considered was using a homegrown teacher model on a simpler data set, something like MNIST or Fashion MNIST. My early tests have shown that even very basic convolutional neural networks, like 2 convolutions and 1 fully connected layer, achieve 95% accuracy on these smaller data sets. And a straightforward neural network, just 2 fully connected layers, still gets 90% accuracy. And these results are pretty ideal for experimenting with knowledge distillation. And I think that the time saved from avoiding deep model training can be redirected to, exploring the topic even further. For example, some things I'm also interested in doing are maybe tuning some of the hyperparameters related to knowledge distillation, like the temperature, for example. So despite the simplicity of, using a simpler data set, since the goal of this project is to demonstrate knowledge distillation, I think that the choice of data set is less important than just showing off the method. So based on these considerations, I've decided to go with the second approach. And that's everything that I have. I have some sources here if anyone's interested in those. And if there's any questions, you can hit me.
Yep, very nice idea. I think it's very relevant when you have to run some deep learning model on like a mobile device or like a remote device, right? And yeah. So you're trying to do essentially a kind of transfer learning, but with sort of a temperature term, in like a KL divergence terms, with like those class distributions, right? And
Yeah, it's not really like a transfer learning, because a transfer learning would, except for like the fully connected layers, it would preserve the size of the model. So this is essentially like during the loss calculation, what you're doing is you're essentially doing a cross entropy between soft teacher models or soft teacher predictions and soft student predictions instead of against like the actual hard predictions. And that way what you're doing is you're just kind of accelerating the training process and maybe even enriching the training process while transferring knowledge into a smaller model. So it has some similar utility to transfer learning, but transfer learning is more about like training models faster, and knowledge distillation is more about decreasing the size of models.
Right. Makes sense. So you don't necessarily have any sort of pre-trained weights for your student model, but rather, it makes sense.
Exactly.
It makes sense. It makes sense.
So I have a question. Could this be used to like save on computational resources in just like larger machines in general, or would you, if you were to keep doing this, would you end up with too much of a loss in accuracy?
Yeah, that's a really good question. So I'm not like an expert on this topic yet, but I would think that if you performed knowledge distillation too many times, like if you like daisy chained knowledge distillation model to model, your predictions would probably become so soft that it would be an entirely uniform distribution and your predictions would be virtually random. So I think this is really good for like a one-off if you're just trying to make a model smaller. I believe that so if you were to example train like your raw student model without knowledge distillation, that should still be faster than if you were to use knowledge distillation, because the knowledge distillation requires an extra prediction being made by the teacher model for every training step. So the training is going to be slower, although, there is a chance that you converge to some optimal weights faster, like in less epochs. So I think it's a trade-off of what you're really looking for. I think that if you have unlimited space on your machine, you might as well just train the biggest, best model you have. And this might not be a useful technique for you.
Thank you.
Thanks, man.
Sorry, I also have a quick questions.
Yeah, what's
Yep.
going on?
So, yeah, I show you that during the training process, you simultaneously training the teacher model and student model, right?
So during the training so we're assuming that the teacher model is pre-trained, and when we're
Oh, I
training when
see.
we're training the student model, we're feeding the training data to the student, but we're also feeding it to the teacher, and the student is making a prediction, and the teacher is also making a prediction. And this distillation loss, this is that second loss term that we're adding to try and make the training more rich, right? So we're not
Okay, got
training
it.
the teacher, but we are making a prediction with the teacher.
Got it. Got it. Thank you so much. That's
Yeah.
a really good idea. Thank you.
All right.
No more questions? Any more questions? All right, if not, thank you for the presentation. It's really interesting.
Yeah. Thanks, guys.